Welcome to Hot Topics. Today's subject will be how a circuit breaker can have 3 to 5 protective levels against current values that build up. Of course, we're going to look at a circuit breaker that just has short circuit, ground fault, and overload protection. Period. That's it. Or we could buy a circuit breaker that has ground fault protection, short circuit current protection, overload protection, plus GFCI. And then on the other hand, we could select a GFCI and purchase it that provides short circuit, ground fault, overload, GFCI, plus AFCI protection. Now, first of all, let's kind of go over some definitions. In Article 100, we'll take a look at our short circuit type currents on page 40, I believe it is, of the NEC. And you can turn to page 40 and look up the definition of a short circuit. And they straighten some things out there in that definition. They're saying, a short circuit can be from an ungrounded conductor to the neutral, or from ungrounded conductor to ungrounded conductor. But a ground fault would be from an ungrounded conductor to grounded metal, raceways, enclosures, and so forth. Now, we know on page 40 we can pick up the definition of short circuit, and on page 49, I believe it is, or maybe page 35, we would pick up the definition of a ground fault. Now, we could also look at 110.12 and 110.7. Look at 110.7 on page 46 of the code, and we would pick up that we're supposed to make sure before we turn the circuit breaker on, if we possibly can, that the circuit is free of short circuit, ground faults, and overloads. We would want to check that out. And of course, we're told to do that in 110.7 around page 46 of your code book. Now, in dealing with overloads, we would look at 210.19A1, and that's around page 65 of the code if you wanted to look that up. And for motors, it's 430.32A1 and C is in car of the code. But an overload, is anything that exceeds basically the 125% rule that we figure our overload protection, 125% of the load. Then, a circuit breaker would have overload protection if we could design it within that value after we do the calculation. Now, reviewing a replacement of a circuit breaker. Say, look at your illustration 8-12. That comes out of our Volume 1, Stallcup's Electrical Design Book, Chapter 8, Figure 8-13 that we're using in the illustration. And notice that we have a long time current rating of the conductor. When you look at the boxed in information with a title head, long time current rating, and a number 10, in accordance with table 310.16 and step 1, a number 10 THHN is only good for 30 amp. Now, I know in the 90-degree column it would have a greater value rating. It had like 40 amps. In the 75-degree column, it'd have like 35 amps. In the 60-degree column, it would have 30 amps. Now, we know that if it's a cable, like non-metallic sheath cable, Romex, or rope you might call it, depending on the part of the country that you're from, notice that 334.80 basically states that all cables are 60 C ampacities unless otherwise stated on the cable. Like service entrance cable, for example, 75 C. So in residential, you usually find 60/75 C rated circuit breakers. And the reason for that naturally you can cable them at 60 degrees C ampacity, or pull conductors in conduit to, like air conditioners or larger pieces of equipment, and use a 75-degree column. So we know we find that in 110.14C1 little a. If you're over 100 amp load, it's automatically 75 degrees C terminals. So your terminal ratings, naturally you look up the requirements in 110.14, C as in car 1, little a or little b, based upon the 100 amp or less rule, or over 100 amp. So we would pick that up. Now you notice the short time current rating. We would go to our Table 8 to Chapter 9 on page 705 of your code book, page 705, I believe. And a number 10 circular mill rating is 10,380. So notice in the formula in step 2 in the boxed in information, we find that current, the short time current rating of that conductor, you take that circular mill rating of 10,380, and if it's an insulated conductor, divide it by 42.3. If the conductor's uninsulated, divide by 30. So when you do the math, you can see that that number 10 would take 245 amps for 5 seconds and never damage the insulation. And of course, in the solution, we look at 240.4D as in dog, and if it's not one of the loads that require the overcurrent device to be size greater than 125%, which we, from our experience, knows that all those loads where you can size up greater than 125% are found in table 240.4G of the code. So since it may be a cable, it would be 60 degrees C ampacity, so you'd have 30 amps long time current rating, but you would have 245 amps for a short time current rating. And then if we took in the square root and took current squared, which would be 245 times 245 times 5, divided by the new clearing time of the overcurrent device, we could put more amps on there. And we'll kind of take a look at that and do that calculation coming up. But now if we review our table and figure 8-13, then notice the quick calc there. You notice you have the circular mill of a number 12 wire, which is 6,530. Divided by 42.3, and it would carry 154 amps for 5 seconds. But not any longer than that, or you damage the insulation. And then if you went over to the quick calc 2 and the square root now, you would have the current squared times the time. So it'd be 154 times 154 that you see here, times 5 seconds, because that's what the 42.3 is based on. And you divide it by the new clearing time. So if you had a half cycle times it'd be 0.0167. You would have 2 cycles times 0.0167, and you'd come up with 0.0084 seconds. Do your math and then take the square root, and you see that that conductor would take 3,757 amp for 0.0084 second and never damage the conductor insulation in any way. And then in step 1, we tell you, for your small conductors, number 10 and smaller, 240.4D, would say the overcurrent device for number 14 wires 15, for number 12 it's 20, for number 10 it's 30. And you can't exceed the overcurrent device rating for those conductors without the load that these conductors supply fall within table 240.4G. Now, You could take a number 10 conductor, and I've kind of done the math here, and the number 10 conductor that we looked at, the current squared would be basically 245 times 245 times 5 seconds, and then you divide that by 42.3, and then you would come up with the amount of amps that you put on. It'd be about 245, as you see in that first drawing, an illustration we looked at, figure 8-12. But when you did the math with a overcurrent device clearing with a half cycle, which is 0.0084 second, as you see in the figure 8-13, the second figure that we looked at. When I did my math there, 245 times 245 times 5 seconds, divide by the new clearing time, 0.0084 second, that number 10 would take 5,977 amps without damage to the installation. But again, it only take it for 0.0084 seconds. Now, we know from our experience a circuit breaker at 600 volts or less will hold about 3 times its rating. So if you had a 30 amp circuit breaker, it'll hold 3 times 30, 90 amps, and it'll hold it for just about, well, it depends on the voltage. If you were 120, 240, or 208, it'll hold for about 9 seconds. If you're 480, 277, approximately 4 to 5 seconds. So your motors and things can start. And so basically, if you had a 30 amp device, circuit breaker, times 3, 90 amps, any motor load or anything that had an inrush value to it, if it was below that 90 and the acceleration time of the load was, quick, fast, then it started. But if we had a 30 amp fuse, you'd use 5. So 5 times 30 would be 150. Now you can see that inrush current could be increased. And that's what this illustration is kind of getting over to you. And just remember, 110.7, around page 46 of your code, says that we as electricians have to ensure that the circuit that we're protecting with that 30 amps overcurrent device, number 10 wire, is free of short circuits, ground faults, and overloads and so forth. Now, we could also pick up the Gfci Protection, and we know that's in 210.8A for dwelling units. 210.8B is in boy for other than dwelling units like commercial or industrial. And then if we want the AFCI protection, we can pick that up in 210.12 of the NEC. Now, what's good about this, we can have just one circuit breaker providing short circuit, ground fault, overload, GFCI, and AFCI, and protect outlets in a dwelling unit, say, that are required to have all this protection. You can get that in one breaker and do the job. So these are the questions that kind of come in occasionally. So I just thought we'd do a hot topic on it. So there you have it. That's what's required. Good luck with your installation and protection of your outlets in a dwelling unit or in commercial or industrial related locations.